So hello everyone. So this is the last slide I have presented, no? And we shall continue now our topic on properties of fluids, no? All right. So we're done with introduction to surface tension. So let's proceed with capillarity, no? So what is capillarity? So this is the ability of a liquid to flow in narrow spaces without the assistance of gravity. Alright? So it's the ability of a liquid to flow in narrow spaces without the assistance of gravity. So, it has something to do with surface tension, no? So we have here. So I've discussed this in detail. Capillarity. If, for instance, okay, uh, we have we have water in container. Okay, so this is water in a container. Okay, and then there is a tube with a small diameter. Insert it was soaked in water, no, soaked below. So now the fluid uh, has the ability to flow, no. So that is its property, no. So it could rise, no, above this level, no. It could rise above this level, okay. So it can be up to here, the fluid that will flow in that narrow space, or the other way around. Instead of rising, it falls, no. So another fluid, for instance, instead of rising, it falls, no. So it becomes, it's here now, okay. It does not rise, it falls. All right. So if this is a reference surface, okay, the liquid surface, okay, so it falls. All right. So that is capillarity. It is the ability of a liquid to flow in narrow spaces without the assistance of gravity. All right. So disregarding gravity, if I insert, no, uh, if I insert a tube, for instance, of small diameter, okay, the tendency is that fluid, or should I say liquid, will rise or fall in this tube. Okay, so we call this tube as capillary tube, because when we talk about capillary, having a small bore, or a uh, small hole, no. Okay, so capillarity can also be called capillary motion. So other term for capillarity, so it can be called capillary motion, capillary action, or wicking. Okay, so capillarity can be called capillary motion, capillary action, or wicking. Now capillary, having a very small bore. So I have mentioned this. So when I talk about bore, I'm pertaining to the small space, no, inside a cylindrical small space inside a cylindrical object, for instance. Okay, small space. Okay, so having a very small bore, no? So that is capillary. That's why it's called capillary tube, because there is very little space inside that tube, no? So here's the illustration. For example, we have water. So this is a property of water wherein it will rise. Okay, when the capillary tube is was immersed, no, okay, in water. Okay, so tendency is that some of the liquid will go up to here, up to this point. Okay, now as you notice, you can see a crescent like figure, no, a crescent like figure. Okay, we call that as meniscus. Okay, we call it as meniscus. Okay, so since this is the direction now, it's now called concave meniscus. Concave meniscus. Okay, so it forms, no, so something like this. It's somewhat like this. Okay, wherein so this is the shape, something like this. All right, concave meniscus. So this is our concave meniscus, no? All right. So as you notice, it rises. If this is water, it will rise above this level, no? In a capillary tube. Okay, without the assistance of gravity. Okay, it rises. All right. So what's the reason behind that? So the reason is that for a capillary tube, for the so there is an interaction between the capillary tube and water, and that interaction between the capillary tube and water is greater than the interaction of water molecules uh, to each other, no? So we have what we call as cohesion. When we talk about cohesion, attraction between two like particles, substances, or objects, no? So we have molecules of water. They attract each other, no? Molecules of water attract each other, okay? They attract each other. However, there's another object, which is a capillary tube, no? There is now an interaction between the capillary tube and water inside this container. And with the presence of this capillary tube, okay, it happened that there was a rise in the in water, no? There's a rise in water in the capillary tube. Okay, so in other words, there is now adhesion. When we talk about adhesion, it is the attraction between two unlike particles, substances, or objects. Okay, so it's the attraction between the capillary tube and water. Attraction between capillary tube and water. Okay, so since in this example, we have water and a capillary tube, okay, it means that uh, for water, we can say that cohesion is less than adhesion, or the other way around, adhesion is greater than cohesion. Okay, so we have cohesive forces, attraction between two like particles, substances, of objects, there is cohesive force. There is also adhesive force, attraction between two, unlike particles or objects, which is water and the tube. So that force is greater than the cohesive force of water. Okay? The adhesive force between water and the tube, which is the capillary tube, is greater than the cohesive force between two between the molecules of water. Okay? So that's the reason behind, no? So let's have another example. All right. So we have here mercury. The substance is mercury. And as you notice, when a capillary tube is with the we put a capillary tube in this container with mercury, and what you have noticed, this is the normal level of mercury, and as you notice, there is there is fall of mercury inside the tube, fall of mercury. Okay, so mercury falls, or there is what we call as capillary capillary fall, no? There is capillary fall. In here there is capillary rise, no? There is height, and there is capillary rise with respect to the liquid surface, right? So this is the liquid surface, and in for a mercury, okay, what happened? The mercury, instead of going up, it goes down, right? So there is capillary fall or capillary depression. So what's the implication? Implication is cohesion is greater than adhesion. Okay? So the attraction between molecules of mercury is greater than the attraction between the capillary tube and mercury. Okay? So the cohesive force, no, that exists between the molecules of mercury is greater than the adhesive force between the capillary tube and mercury. Okay? So that's it, no? So we now proceed. So we analyze now. So we have here a certain liquid, and there is capillary rise, and this is the tube with the diameter equals to twice the radius of this hollow tube. No, it's a hollow tube. No, and we have here capillary rise or fall. The capillary rise or fall in a tube is given by an approximated value h. So how do we compute for h? The capillary rise or fall in a tube, no? So that can be obtained by using this formula. 2 multiplied by the surface tension, or it can also be called coefficient of surface tension, denoted by sigma, the Greek letter sigma, no? Multiplied multiply it by cosine theta, which we call as the contact angle or the wetting angle. So if we will extend this, no? So if we will extend this, okay, so at this point, okay, so let me write, ayan, ayan, okay, All right, so at this point, okay, so we extend this line. So there is angle theta there, and this is also angle theta. Okay, in geometry, vertical angles are equal in measure, right? These are called vertical angles, and they are equal in measure. So this is now the contact angle, or what we call as the wetting angle, no? Cosine of theta, cosine of the wetting angle, or the contact angle, okay, between uh, at this point, no? All right, between tube, between the tube and water, no? Sorry, between the tube and liquid and the liquid here. It can be water or any, no? It depends. Okay. So and then we divide it by the specific weight of the substance here, the liquid substance, no? In this diagram, no? And the radius multiplied by the radius of this tube, no? So take note that, as I have mentioned, h is height of capillary rise or the fall, capillary rise or depression, no? Capillary depression. If if the height is positive, that is capillary rise. If the height is negative, we call it. It implies that there is capillary fall or capillary depression. And sigma st is the surface tension or the coefficient of surface tension. Gamma, as I have said, is the unit weight of the liquid or the specific weight. Theta is the contact or wetting angle. No, R is called the radius of the tube. No, of the capillary tube. No, and take note, for water in a clean tube, the angle is zero. Okay, the angle is zero if this is water in a clean tube. So in other words, if that is zero, this will be the direction of the surface tension force. This will be the direction of the surface tension force. Okay, because the water, the angle is zero. Okay, if the angle is not zero, this is the direction of the surface tension force. Okay, the surface tension force. All right, so that is the direction of the surface tension force, the force due to surface tension. Okay, I hope you get it, no? And also, if we have mercury in a clean tube, okay, that angle is 140 degrees. Okay, if it is a clean tube. All right, and take note, if H is positive, as I have mentioned, that is capillary rise, and if it is negative, that is capillary fall or depression. All right, sometimes instead of radius, okay, we use the diameter. And in terms of diameter, this is the formula. Because the radius is equal to half of the diameter, right? That's why this becomes d over 2. Then there's 2 and there is 2 here. We multiply, so we get 4. So that's the new formula in terms of diameter. Okay? So diameter of the tube. So let's answer a problem regarding capillary action. So estimate the height to which water at 70 degrees Fahrenheit will rise in a capillary tube of diameter 0.12 inches. The surface tension and specific weight of water at 70 degree Fahrenheit are 0.00497 pound per foot and 62.3 pound per cubic foot respectively. Assume the tube is clean. Alright, let's answer. Okay, so we have here, assume the tube is clean. So we have water and there is a tube, no? And this there is rise, no? Estimate the height of each water will rise. So this is now age, no? We're looking for age. Okay? So at the temperature of 70 degree Fahrenheit as mentioned in the problem. And there is diameter of 0.12 inch, no? Diameter of the tube of 0.12 inch. And we're looking the surface tension at this temperature, 70 degree Fahrenheit, is 0.00497 pound per foot. And the unit weight or the specific weight of water at 70 degree Fahrenheit is 62.3 pounds per cubic foot. Okay, now, so let's go back before I proceed. Okay, I'll just, alright, so we can now proceed. Okay, alright, so this is the given. These are the given, and this is the formula in finding the height in a capillary tube of the substance, of the liquid substance. And we apply, but before that, since this is water in a clean tube, automatically that will be zero. The angle is zero. So therefore, this is the direction of the force due to surface tension. Okay, this is the direction of the force due to surface tension. And we have, so that is zero. Okay, this is zero. And the radius is half of the diameter. Okay, so we have now this. The surface tension is 0.00497 pound per foot. Cosine of 0 all over 62.3 pound per cubic foot. Specific weight of the substance, which is water. And the radius, we just divide by 2 the diameter. So 0.12 over 2. So as you notice, we can eliminate pounds, no? And there is foot, cubic feet, or cubic foot, and inches, and inch. So we should be consistent with the unit. This is a unit of length, foot. So let us transform inches into foot, no? Transform inch to foot. So let's analyze this. So for every 1 foot, there are 12 inches for every 1 foot. Okay, so 1 foot is equals to 12 inches. So therefore, we can eliminate inches, and we are now consistent, no? So what is the final unit for this? Okay, so unit tricks tayo. 1 over foot times, cancel na yon, 1 over foot. Okay, 1 over foot, and then 1 over cubic foot. Okay, meron ka dito 1 over cubic foot. Then meron ka ditong foot. Okay. So ano yung magiging unit niyan? Okay, so 1 over foot, 1 over 1 foot over feet cube, 1 over feet squared, right? 1 over foot squared. Okay. So if meron kang A over B, di ba divide C over D, that is simply A over B times D over C. That is basic in algebra, right? So meron ka ngayong 1 over foot times foot squared over 1. Foot squared over 1. And foot squared over foot. Okay? That's it. So the unit is foot. So we have our answer of 0.0319 foot. Okay, and for every foot, 12 inches, we just multiply this by 12, we get 0.383 inch. So that is our answer. No? Alright, so that is the capillary rise of water. So let's answer number 2. Estimate the capillary depression for mercury in a glass capillary tube 1 millimeter in radius. Use the surface tension coefficient 0.514 Newton per meter and an angle of 140 degrees. For mercury, the specific gravity is equal to 13.6. So let's analyze. So this is mercury, okay, and there is a capillary tube, okay, and there is capillary depression, no? Bumaba yung mercury dito sa part ng tube, no? So in this case, where we are, our interest is to find for this height, the capillary depression, okay? And we are expecting the value of H to be negative because this is our reference. This is zero height. And from this going down, we get negative. That's why if our goal is to find the capillary depression, we have to take the absolute value, and because our concern is the magnitude only and not the sign, no? Estimate the capillary depression for mercury. Okay, so the capillary depression magnitude is to be found. Okay, so we have the diameter, or should I say the diameter, which is twice the radius. Okay, the radius in this example is 1 millimeter, and the surface tension is 0.514 Newton per meter. Okay, so if we have for the contact angle or the wetting angle 140 degrees, so from this point we draw a line, and this is the angle theta, which is 140 degrees. Okay, and this is also angle theta, which is 140 degrees. Okay, so this is the contact angle, and which is 140 degrees. And we have the specific gravity of mercury of 13.6. Solution to the problem. Let's find for age, but let's find for the absolute value of age. But first we find for age, we solve. So take note that our substance is mercury. Okay, and the radius is indicated. Okay, so our substance is mercury, and take note that the specific weight of mercury is not given in the problem. What is given is the specific gravity. And we have to recall that specific gravity of the substance is simply equal to the unit weight of the substance over unit weight of water at a certain temperature. Okay? So since in the problem the temperature is not indicated, so we'll use the standard temperature for the specific weight of water, which is at 4 degrees Celsius. Okay, so unit weight over unit weight of water at 4 degrees Celsius, or Federal density. No? Okay, Federal density. So yan ang pagkuha ng specific gravity ng isang substance. So we have, therefore, if this is mercury, no? If that is mercury, no? So unit weight of mercury over unit weight of water at 4 degrees Celsius, we just multiply the specific gravity of mercury and the unit weight of water at 4 degrees Celsius to get the unit weight of mercury. There. That's why its specific gravity of mercury multiplied by the unit weight of water at 4 degrees Celsius will obtain the unit weight of mercury. Then we multiply it by the radius of the tube. Okay? So we now substitute the values. So we have the surface tension. Okay, then 140 degrees. Specific gravity. Oh, take note that the unit weight of water at 4 degrees Celsius in my discussion, in my previous discussion, that is at 4 degrees Celsius, that is 9.81 kilonewton per cubic meter, and that is 9,810 newtons per cubic meter. So we have this. Okay, and then the radius is 1 millimeter. We express it to meter. And we'll get an answer of negative 5.90 times 10 to the negative 3 meter. Okay, and we are expecting the answer to be negative because there is capillary depression, right? And we're looking for the absolute value of H. So, by the way, since this is 10 to the negative 3, that is milli. Okay? In my previous discussion, I have introduced the suffixes, no? Or should I say prefixes, no? The prefixes. So this is millimeter, mm, the prefixes. So this is millimeter. 10 to the negative 3 is milli. And then we get the absolute value of H. We get positive 5.90 mn. So this is now the capillary depression, the magnitude, no? So 5.90 mm. So there is a fall of 5.90 millimeters. Okay? So in other words, there is a rise of negative 5.90 millimeter. If there is a rise of negative 5.90 millimeters of mercury, that means that there is a fall of 5.90 millimeters of mercury. Okay? That's the interpretation to that. No? So pag sinabi yung negative rise, that is fall. Okay? So we can proceed. Alright, so let's go to the next topic, liquid compressibility. So when we talk about compressibility of a liquid, this is the property of liquid to change volume under action of pressure. Okay? So it's the property of a liquid, no? To change volume under action of pressure. For example, if I have a container, okay, if I have a container containing water in it, and I have a compressor, okay, if I have a compressor, okay, I have a compressor, I push, I exert a force, okay, I exert a force, so that water here will be compressed. Okay, the liquid here will be compressed. So there is now a property of liquid that we call compressibility. No, because if I exert a force, there will be change in pressure here. Change in pressure in the of water because I exerted the force. Okay, there's a change of pressure. So, naaral nyo naman yung strength of materials, uh, yung deformable, yung mechanics of deformable bodies, yun yung strength of materials. Naaral nyo na rin yung thermodynamics. So, familiar na kayo kung ano yung pressure, right? Okay? So, there is now pressure here. Kasi pag yung container hindi nakayanan yung pressure nito, mabubutas yung container, right? So, kaya kailangan kahayanan niya yung pressure dito sa loob, no, ng container. So, dahil may pressure dito, no, magdudulot yun ng stress sa container. Okay? Magdudulot yun ng stress sa container. So, magkakaroon ng change in pressure ngayon. Okay? Magkakaroon ngayon ng change in pressure. At kapag nagkaroon ng change in pressure, kaakibat nun, change in volume. Okay? Kapag may change in pressure, may change in volume. Okay? Hindi pwedeng walang change in volume yon kasi mechanical eh. Take note at a constant temperature. At a constant temperature only, no? At a constant temperature, pag nag-exert ako ng force, magkaka-change in pressure, magkaka-change in volume. Okay? Magkaka-change in pressure, magkaka-change in volume. So, ngayon, meron tinatawag na compressibility of a liquid. This is the property of liquid to change volume under action of pressure. Okay? So, dahil nagbago yung pressure, magbabago din yung volume. No? So, ngayon, compressibility is the property of liquid to change volume under the action of pressure. So, how do we measure now compressibility? So, ito lang yung formula natin. Okay? So, ito yung illustration ko kanina. So, nag-exert ako ng force. Ipo-compress natin yung tubig. Yung liquid. And, kapag kinompress mo, magkakaroon ng pagbabago sa volume sa loob. Yung volume sa loob, magbabago. Magbabago din yung pressure. No? So, meron itong volume and pressure. So, compressibility of a liquid, ito yung kanyang definition na iba, is also the negative fractional change of the volume of the liquid per unit change in pressure in a constant temperature process. Okay? Setting formula. Negative fractional change of the volume of the liquid. So actually, okay, beta is negative dV over V all over dP. Yan ang kanyang formula. Okay? Negative dV over V all over dP. So that is compressibility. Okay? So, in this case, no, uh, so paano siya naging negative dV V dP? O, inano lang natin yan. Inayos lang natin negative dV V dP. So, yung over V, lalagay natin sa denominator. Pareho lang yan. Okay? Negative dV over V dP. Okay? And then, beta, other formula. Okay? In this na lagay natin ay D, no? pwedeng lagay natin ay delta, no? Change. Change in volume. Okay? Ito ay differential volume, dV. Yung dP, differential pressure. Okay? Negative differential volume all over V times differential pressure. Pag sinabi nating differential, infinitesimal change yun. Okay? Infinitesimal change. Ibig sabihin, the limit of delta V over delta P as delta P approaches 0. Okay, which is dV over dP. Okay? Infinitesimal change. Ibig sabihin yung delta P ay nag-approach ng 0. No? So, kung nag-approach yun ng 0, so dV over dP yun. No? Okay? So, ito nga, dV is infinitesimal change in volume. Okay? So, walang katapusang pagliit sa volume. Diba? 0.01. Okay? dV equals 0.01 cubic meter. Eh, meron pang maliit dyan. 0.001. Eh, may mas maliit pa dyan. 0.000001. No? Eh, may mas maliit pa dyan. Walang katupusan na pagliit na maliit. Kahit 1,000,000 zero, pwede. No? Walang katapusan. Okay? So, ang tawag doon, infinitesimal change in volume. No? Or differential volume. Okay? And then, we have also V as the original volume. Okay? We have the original volume. And ito yun. dP, infinitesimal change in pressure. Okay? dP, pag sinabi natin dP, differential pressure. Okay? Sabihin yan, halimbawa, 0.01 Pascal. No? May mas maliit pa dyan, 0.000001 Pascal. May mas maliit pa dyan. No? So, that is differential pressure or infinitesimal change in pressure. Pag sinabing infinitesimal, walang katapusan na pagliit, di ba? Infinitesimal. So, delta P, change in pressure. Okay? Pag delta P, change in pressure. No? Sabihin, definite change siya. Hindi siya infinitesimal change. Definite change. Ito, definite change in volume, definite change in pressure. Ito yung beta natin, compressibility or coefficient of compressibility. So, yan yung formula ng pagkuha ng ating liquid compressibility. Okay? So, ayusin ko lang. So, we now proceed. Okay. So, let's now study about bulk modulus of elasticity. O, pag sinabi nating bulk modulus of elasticity, reciprocal of compressibility yan. No? So, ito yung notation natin. E, tapos may subscript na paganyan. Ang tawag dyan ay upsilon. Greek letter upsilon. No? Okay? Which is 1 over beta. Yung ating Greek letter beta. No? Greek letter beta. So, 1 over beta, 1 over the compressibility, no? Or tinatawag din coefficient of compressibility. So, ganyan lang pagkuha ng ating bulk modulus of elasticity. Or, imbis na negative dV over V all over dP, Sulat natin ay negative dP all over dV over V. Ang purpose ng negative, para maging positive yung ating sagot, no? Para sa compressibility at para sa modulus of elasticity. Kasi, kapag may change in pressure, no? Pwedeng positive yon or pwedeng negative. Pagka positive ang change in pressure, negative change in volume, no? Or pag naman negative ang change in pressure, positive change in volume. Kaya baliktaran sila ng sign, kaya kailangan may negative yan para maging positive, no? O kaya naman, kung definite change ang pinag-uusapan, hindi infinitesimal change, so we have negative delta P all over delta V over V. So, ulitin ko, delta V, new volume minus the original volume, no? Delta P, new pressure minus the original pressure. Okay? So, let's answer a problem. A rigid steel container is partially filled with the liquid at 15 atmosphere. The volume of the liquid is 1.3200 liter. At a pressure of 30 atm, the volume of the liquid is 1.231 liter. Find the average bulk modulus of elasticity of the liquid over the given range of pressure if the temperature after compression is allowed to return to its initial value. What is the coefficient of compressibility? Okay. So, dalawa yung tanong, bulk modulus of elasticity at saka coefficient of compressibility. So, given natin, we have a rigid steel container. So, ito yon. It's partially filled with the liquid. Ito yon. At 15 atmosphere. So, the pressure is 15 atmosphere. Ang ATM ay unit of pressure called atmosphere. Alam niyo yan sa thermodynamics. Naaral niyo siguro yan, no? The volume of the liquid is 1.3200 liter. Okay, so this is the volume of the liquid, no? Okay? At the pressure of 30 atm, so isabihin niyan, kinompress kasi nagkaroon ng pressure ng 30 atm. Okay? Kung hindi mo i-compress yan, hindi lalaki ang pressure. So, kailangan i-compress. At the pressure of 30 atmosphere, okay, the pressure, so ito yon. So, lalagay natin P prime kasi new pressure. Okay? The volume of the liquid is 1.231 liters. So, lumiit yung volume. Lumaki yung pressure, lumiit ang volume. That's natural. Find the average bulk modulus of elasticity. So, hinahanap natin the average bulk modulus of elasticity. No? Okay. So, yung average bulk modulus of elasticity, ito yon. So, sabihin, pag average, gagawin natin yung delta. Yung delta V, yung delta P over negative delta dV over V. Negative delta V over V. Yan. Delta yung symbol kasi average, no? Pag instantaneous, dP on. dP over negative dV over V. Instantaneous bulk modulus. Okay? So, we can now proceed, no? So, required E sub epsilon. Ito yung nahanap natin, the average bulk modulus of elasticity. And we have the coefficient of compressibility, beta. The coefficient of compressibility. No? So, alam natin na negative delta P over delta V over V, yun ang formula. ng ating bulk modulus of elasticity. Okay? So, delta P is new pressure minus original pressure. Delta V is new volume minus original volume all over the original volume. Ito. So, P new is P prime, P original is P, V new is V prime, V original is V, all over V. At alam natin, ito yung mga nakuha nating, ito yung mga given sa problem. Okay? Substitute natin, negative of 30 minus 15 atmosphere all over 1.231 minus 1.232 liters over 1.232 liters. Okay? So note lang that 1 atmosphere is 101,325 Pascal. Naaral nyo yan sa termo siguro. Ang 1 atmosphere ay 101,325 Pascal. Okay, multiply natin. 101,325 Pascal for every atmosphere. So we have 1.87249 times 10 to the 9 Pascal. Okay? So that is our answer. No? So check natin using calculator. Okay? So we have 30 minus negative. Sama na natin yung negative, no? Negative. So 30 minus 15. 30 minus 15. Okay? Over. Meron ka doon. Meron kang fraction. So 1.231 minus 1.232. Okay? Over 1.232 sa ilalim. 1.232. Then, meron kang i-multiply dito sa main fraction. Okay? So, ano yung i-multiply natin? 101. Para ma-convert siya ng Pascal. No? Yung atmosphere. 101,325. Okay? Over 1. Over 1. 180 m. Tapos, equals, ayan. So, ang daming digits, right? So, ang gawin nyo, para di kayo mahirapan, pindutin nyo yung ENG. Ito. Ayan. 1.87249. Okay. Times 10 to the 9 Pascal. Yun ang unit. Diba? Cancel lang ATM, cancel lang liter, Pascal lang unit. So, that's a unit of the bulk modulus of elasticity. At ang 10 to the 9 ay giga. Kaya 1.87249 gigapascal. Okay, GPA. Okay? So, next, note that for every the bulk, ang hinahanap naman natin ay bulk modulus of elasticity. No? So, bulk modulus of elasticity. So, hinahanap natin ay bulk modulus of elasticity. Recall natin that ang hinahanap natin ngayon ay compressibility, no? Compressibility, tapos na tayo sa paghanap ng bulk modulus of elasticity. So, recall natin yung formula ng bulk modulus of elasticity, that is equals to 1 over the compressibility or the coefficient of compressibility. So, therefore, the coefficient of compressibility is equal to 1 over the bulk modulus of elasticity. Sabihin niyan, reciprocal of the bulk modulus of elasticity is the coefficient of compressibility. So that is 1 over 1.87249 times 10 to the 9 Pascal. At ang sagot ay, so ang unit niyan ay square meter per Newton. So makakancel ang Pascal. No? Cancel ang Pascal. Okay? So tapos, ang bibigay na sagot ay 5.34048 times 10 to the negative 10 square meter per Newton. Paano siya naging ganon? So, meron kang 1, wala nang unit sa numerator, tapos dito cancel. Meron ka dito Newton per square meter. So, sabihin niya, reciprocal na Newton per square meter per Newton, no? Square meter per Newton. Okay? Kaya meron kang square meter per Newton. Okay? So, check natin. So, let's check. So, 1 over 1.87249 raised to 9, no? 5.34048 times 10 to the negative 10 square meter per Newton. Okay, I hope you get it. So we can now proceed. So problem 2, find the change in volume of 1 cubic foot of water at 80 degree Fahrenheit when subjected to a pressure increase of 300 psi. The bulk modulus of elasticity at 80 degrees Fahrenheit is 325,000 psi. So required, the change in volume. Yun ang ating concern. So kung ito yung ating figure, no? Wherein meron ditong water being compressed. Water na naka-compressed, I mean. So ano raw yung change in volume? Okay? Pag may change in volume, isabihin niyan, nagkaroon ng, so meron kang initial condition and final condition. Kasi may change in volume. So sabihin niyan, find the change in volume of 1 cubic foot of water. So sabihin niyan, ito yung original volume of water. Okay? Ito yung original. Base sa statement. Find the change in volume of 1 cubic foot of water. So, ito yung original na diagram. Okay? Ngayon, ito yung volume na 1 cubic foot. No? So, this is condition 1 now. So, at 80 degrees Fahrenheit, the temperature of the water here is 80 degrees Fahrenheit. When subjected to a pressure increase. So, kung may pressure increase, ibig sabihin, kinompress itong tubig na to. Kinompress. So, kung may kinompress, merong compressive force na in-apply. Right? So, sabihin, so, when subjected to a pressure increase of 300 psi, so, there's change in pressure. So, ibig sabihin, from lower pressure to a higher pressure. So, from lower pressure to a higher pressure. So, ibig sabihin, lower pressure yung condition 1, higher pressure yung condition 2. So, ibig sabihin, para magawa yon, dapat i-compress natin para ma-achieve yung positive change in pressure. No? So, ibig sabihin niya, it is compressed. Okay? It is compressed. No? So, kinompress natin, okay, para ma-attain natin yung objective na magkaroon ng positive 300 psi change in pressure. Okay? So, ito yung original pressure. Ito yung ating final pressure. Ito din yung ating final volume. Okay? So, wherein, since positive ang change in pressure, ina-expect natin sagot Sa change in volume ay negative. Baliktaran ng sign yan. No? So, pag kinompress mo, lalaki yung pressure, pero lilit ang volume at 80 degrees Fahrenheit. Basta na-maintain yung temperature na 80 degrees Fahrenheit. So, the bulk modulus of elasticity at 80 degrees Fahrenheit is equals to 325,000 psi. So, yun ang given. Solution. By formula, the average bulk modulus of elasticity, no, is equals to negative delta P over delta V over V. No? So, therefore, ayusin natin ng pagkakasulat. So, yung meron siyang over V, pwede ko naman lagay sa numerator, negative V delta P over delta V yan. No? So, ang concern ko ay mahanap yung delta V. So, delta V is equals to negative V delta P all over E sub epsilon. No? So, alam natin that the original volume is 1 cubic foot. Change in pressure is positive 300 psi. The bulk modulus of elasticity at 80 degree Fahrenheit is 325,000 psi, giving us an answer of negative 9.23 times 10 to the negative 4 cubic foot. No? So that is the change in volume. Okay? So tama yung in-expect natin, negative. Implying that there is a decrease, no? There is a decrease in volume because there is an increase in pressure. Okay? So that ends my presentation. I hope you get it. No? Alright. So using ko lang to. So this is problem 2. Okay. This is problem 1, then problem 2. So good day everyone.